Okay, so far we've given the definition of addition in terms of our natural numbers and our counting function sigma on them, and we've also established two very useful properties of addition: that it is associative, meaning that you're free to regroup the parentheses as you'd like, as long as you keep the left to right ordering the same. But in fact, if you wanted to mess with the left to right ordering, the commutative property of addition says that you're free to swap around the order of elements as well. And what these two properties together will imply is that if you have some long string of numbers to be added together, that you can freely rearrange them as you would like, and the result will not change at all. You can add in parentheses however you want, and the final result that you get after doing all your additions in whatever order you wanted, will always be the same. And in fact, it is because addition is both commutative and associative that we can unambiguously write an expression like this without parentheses. Because if we weren't free to just regroup the parentheses and reorder our elements, then this would be an ambiguous expression. Am I supposed to do this first? Am I supposed to do that first? Things like order of operations will kind of clarify, but again, that just kind of establishes a convention for where to place your implicit parentheses, as opposed to removing the need for them. So in this video, we're going to add a third property of addition, and that is that it is cancellative. And what this is it's really a logical implication. So if we know that a plus c equals b plus c, of course for some triplet of natural numbers a, b, and c, then it must be true that a equals b. Now, from the fact that we probably all taken middle school or grade school algebra, you might say that, oh, that's easy to prove, just subtract c from both sides. Well, the problem is we haven't defined subtraction yet. We haven't defined the notion of negative numbers, though we will. And in fact, it's entirely possible to prove this cancellative law for an algebraic system that doesn't have the notion of subtraction or negatives, like addition on the natural numbers. But it still holds that we can, in an expression like this, we can cancel c out from both sides. We'll see how to establish this without appealing to subtraction or negation. And of course, it's going to be done via induction, specifically on c. So our base case is when c is equal to 0. That means that we are trying to show that if a plus 0 equals b plus 0, then a equals b. Remember, we're proving a logical implication here. So the goal of this is not to prove that a plus 0 equals b plus 0, but that if we are given that this is true, then that will follow. It's really this then that we're trying to prove here. So we're just going to start with the assumption that a plus 0 is equal to b plus 0, and we need to show that this entails a equaling b. So transforming both sides of this equation, this gives us sigma applied 0 times to a equals sigma applied 0 times to b. But since applying any function 0 times to its input, we defined that to be the same as doing nothing to it. This gets us back a on the right, or on the left, and it gives us back b on the right. And so the result is that a is in fact equal to b. Now, we're going to move over to the right side for the inductive step, where we get to assume that for all a and b in the naturals, and some fixed c in the naturals, that a plus c equaling b plus c, or rather if that's true, then a must equal b. And we need to show that a plus sigma of c is equal to b plus sigma of c. And how we're going to do that is, or rather show that if this is true, then we can also use this to entail that a equals b. So once again, since we're proving this implication, we get to just start with the assumption that it is true. Equals b plus sigma of c. Transforming both sides the same way, using the definition of addition, this is sigma applied sigma of c times to a equals sigma applied that many times to b as well. We get to pull down the sigma up there and apply the function one more time to itself. So this is sigma applied to the result of having applied sigma c times to a. That is really a mouthful to say each time. And on the right side, it's going to be the same thing, except that's all being done to b. Now regrouping again with our definition of addition, we're going to regroup the terms inside the parentheses, into a plus c equals sigma of b plus c. Now this lets us say, since we know that the result of applying sigma to this expression is the same as the result of applying sigma to that expression, this must mean that the inputs to sigma on both sides of this equation were equal. And this is because sigma is injective. And just to refresh your memory, an injective function is one where if you know that the result of the function is the same, then you know that the inputs must have been the same. You feed two inputs into a function, you get the same result. You must have put in the same input twice. So that's how we get to this conclusion. But from our inductive hypothesis, we know this entails that a equals b, and this is because of our inductive hypothesis. And with that, we have established that addition is in fact cancellative. See you next time.